Okay, so let's jump straight into it. So thermal boundary layer, just as we've seen with the velocity boundary layer, when fluid flows over a surface, a thermal boundary layer would develop whenever there's a temperature difference between the surface and the free stream temperature. So consider flow over an isothermal plate. And we say an isothermal plate just so that we can make it easier for everybody right now. So let's say you have a plate that has a constant temperature, and you have a free stream temperature noted as T infinity. Now at the leading edge, the free stream temperature profile is known because everywhere along the y-axis, the temperature is the same. Over here, everywhere along the y-axis, before you start contacting that surface, will be the same essentially. Now, when fluid particles come into contact with the surface, then they reach thermal equilibrium with the wall. So just how we have the no-slip condition at the surface, we also assume that in terms of heat transfer, that at the surface of the wall, you have thermal equilibrium, and so the temperature at y equals 0 is essentially the temperature of the surface. Now, these particles then exchange energy with the neighboring fluid layers, causing a temperature gradient to develop normal to the surface. So essentially, exactly how I explained the molecular diffusion, whereby you had a net exchange in momentum because you had slower velocity molecules colliding with higher velocity molecules, adjacent to it. You also essentially, when that happens, you also have an exchange of heat transfer. And so the region of the fluid where this temperature gradient exists would also now be called the thermal boundary layer. Hello everyone, I'm Amr, a chemical engineer, been working in the engineering consulting industry for about 8 years now. My goal is to bridge the gap between academia and industry, between theory and practice, and give you the tools you need to succeed as an engineer. So if you want to succeed as an engineer, check me out. And the definition of the thermal boundary layer thickness here is essentially the location, the vertical distance above the flat plate, where that temperature reading is essentially only within 1% of the change of the free stream temperature relative to the surface temperature. And you could use this equation to figure out what temperature that must be. And essentially outside this region, the temperature gradients are negligible. And as you can see, that the whole point of the thermal boundary layer thickness definition is it's trying to pick a point after which you could assume that the fluid assumes the bulk flow conditions and that the impact of any diffusion is negligible. So let's look at the heat transfer mechanism at the wall. So at the surface, the fluid velocity is 0. So energy transfer only occurs by conduction. So the local surface heat flux is therefore given to us by Fourier's law, where you have the heat flux is equal to -1 times the thermal conductivity of the fluid multiplied by the temperature gradient at the wall evaluated at the surface in the y direction. And some people confuse the thermal conductivity here with the thermal conductivity of the solid. No, this is the thermal conductivity of the fluid. And another thing that people confuse is they think that this temperature gradient is relative to the x-axis, but this is actually the change in the temperature gradient in the y direction, because you have heat transfer that is occurring in the y direction due to the diffusivity, and you also have the advection bulk motion, which we're going to look at together. So this is the heat flux that occurs at the surface. Now, using Newton's law of cooling, We also know that the heat flux can be represented by the heat transfer coefficient that represents the effectiveness of the molecular diffusivity and advection that is occurring from the surface to the bulk of the fluid. And so you would write this in this same way, where you have the heat flux is equal to the convective heat transfer coefficient multiplied by the difference in the temperature from the surface to the bulk of the fluid. Now, if you combine these two expressions, then you get the local heat transfer coefficient, and you get to see that it depends directly on the temperature gradient on the wall. So you get to solve for the heat transfer coefficient. So what I did here is I just put these two equations equal to each other, and I rearranged to isolate for the local heat transfer coefficient, and then you essentially get this expression where the heat transfer coefficient is equal to -1 multiplied by the thermal conductivity of the fluid over the difference in the temperature from the surface to the bulk of the fluid, and all that is multiplied by the gradient of the temperature evaluated at the surface in the y direction. So now that we have this equation, let's see how we could understand and solve this equation, perhaps. So first, let us understand the boundary layer, the growth of the thermal boundary layer, because as we've seen with the velocity boundary layer, that it was increasing as the distance traveled by the fluid kept on increasing. So similarly here, as distance from the leading edge increases, what you have is the region of the fluid affected by the wall temperature extends farther into the free stream. So essentially you have the boundary thickness expanding as x increases. And this makes sense because as you increase in the x direction, I've showed you earlier the Reynolds number. So the Reynolds number is dependent on x, which is the distance from the leading edge. So as the distance from the leading edge keeps on increasing, what happens is you have a higher turbulent flow that starts occurring. So yes, you have a laminar region and you have a transitional region, and then you have a turbulent region. And so as the Reynolds number keeps on increasing, then you have more of a turbulent mixing. And if you have more turbulent mixing, then you have more effective, essentially, heat transfer. And also because of that, you have the temperature gradient at the wall decreasing. So the temperature gradient keeps on decreasing as x increases. This is similar to the shear stress, where you had the velocity gradient weakens as it travels further down the plate. Now, once you start switching from laminar to turbulent, the same phenomena happens where you'll get a spike in the temperature gradient, and therefore you're going to get a spike in the local heat transfer coefficient. But then after that, it's going to start decreasing again, and I'll show you a graph that represents that. So because the wall temperature difference stays constant throughout, I said this is an isothermal plate, and we have a constant bulk temperature, then a decreasing wall temperature gradient over here is going to result in decrease in the local heat transfer coefficient. And if the local heat transfer coefficient starts decreasing, then you're going to have your heat flux start decreasing as well. So that is the consequence of an isothermal plate.